Yes, a loose joint in an electrical circuit can indeed cause overamperage. When a joint becomes loose, it introduces a point of high resistance into the circuit. This increased resistance forces the electrical current to flow through a constricted area, which in turn generates a significant amount of heat. The excessive heat can lead to the wires overheating, potentially melting the insulation, and ultimately resulting in a short circuit, which then causes the circuit breaker to trip. In the scenario described at the storage company, it's plausible that a loose joint within one of the underground conduit runs is the culprit behind the overamperage. When the circular saw was plugged in and used, it demanded a substantial amount of current. This surge in current likely exacerbated the issue at the loose joint, causing it to overheat rapidly and triggering the circuit breaker to trip as a safety measure. To effectively troubleshoot this issue, you'll need to employ a multimeter to meticulously check the resistance of various joints within the underground conduits. If you identify any joints exhibiting abnormally high resistance, it indicates a problem that needs to be addressed. The solution involves either tightening the loose connections at those joints to ensure a secure and continuous electrical pathway, or if the joint is too damaged or corroded, replacing it entirely to eliminate the high resistance point and restore the circuit's integrity. Firstly, ensure the circuit is de-energized and properly locked out before beginning any electrical work. This is a critical safety step. Secondly, use a multimeter to test the resistance of each joint in the underground conduit. Look for unusually high resistance readings indicating a loose or corroded connection. Thirdly, tighten any loose connections you find, ensuring they are secure and making good contact. Fourthly, if a joint is severely corroded or damaged, replace it with a new one, using appropriate connectors and ensuring a tight, waterproof seal. Fifthly, once you have addressed all the identified loose joints, re-energize the circuit and monitor the amperage draw. If the overamperage issue is resolved, the circuit should operate normally without tripping the breaker. Remember that proper electrical connections are crucial for safety and efficient operation. Ignoring loose joints can lead to more serious problems, including fire hazards. In this situation with the storage company, let's consider the specifics of the setup to further understand the potential impact of a loose connection. The circuit is a 20 amp circuit wired with number 10 American wire gauge THHN wire, run underground in polyvinyl chloride conduit. It supplies power to 3 buildings, each equipped with 8 100-watt metal halide fixtures for a total of 24 fixtures. There is also a convenience outlet on the middle building. The conduit rises from the ground into a junction box, or JB, located inside a corner storage unit of each building. From this JB, the conduit runs back underground to the next building in the sequence. Inside each building, the power then goes from the corner JB through another conduit run to a central JB, which distributes power to the individual lights in the building. Given this arrangement, a loose connection at any point in this circuit could cause problems, but the location of the loose connection will affect the symptoms observed. Let's examine some potential locations and their consequences. A loose connection at the breaker in the panel would affect the entire circuit, potentially causing voltage drops and overheating at the breaker itself. This could lead to the breaker tripping erratically, especially under heavy loads. A loose connection in the first JB, where the conduit enters the first building, would affect all the lights and the outlet downstream. This could cause the lights in all 3 buildings to flicker or dim, and the outlet might not function correctly. The overamperage condition might be more pronounced when the saw is used, as the increased current draw exacerbates the poor connection. A loose connection in the underground conduit between buildings would affect the buildings downstream. For example, a loose connection between the first and second building would impact the lights and outlets in the second and third buildings, but not the first. This could explain why the wall packs on the same building and the one downstream went out when the saw was used. A loose connection in the central JB within each building would only affect the lights on that specific building. This could cause individual lights to flicker or fail, but it wouldn't necessarily affect the other buildings. A loose connection at an individual light fixture would only affect that light. This is less likely to cause a circuit-wide overamperage condition unless multiple lights have loose connections. The fact that the breaker is tripping and that the lights went out in the same building and the one downstream when the saw was used suggests that the loose connection is likely located somewhere upstream of the middle building, possibly in the underground conduit between the first and second buildings, or in the initial JB in the first building. Here is a step-by-step approach to troubleshooting this situation, building upon the initial advice. Firstly, as always, ensure the circuit is de-energized and locked out for safety. Secondly, inspect the breaker in the panel. Check for any signs of overheating, loose connections, or damage. Tighten the connections and ensure the breaker is properly seated in the panel. Thirdly, systematically check each JB, starting with the first one in the first building. Look for loose wires, corroded connections, or signs of overheating. Tighten all connections and replace any damaged components. Fourthly, focus on the underground conduit runs. These are the most likely source of the problem, given the symptoms. Use a cable locator to trace the conduit path and identify any potential points of damage or corrosion. Fifthly, at each JB, use a multimeter to measure the voltage and current on each wire. This can help pinpoint the location of the loose connection. A significant voltage drop or an unusually high current reading indicates a problem. Sixthly, pay close attention to the neutral connections. Loose neutral connections can cause unusual voltage fluctuations and can lead to equipment damage. Seventhly, after tightening all connections and replacing any damaged components, re-energize the circuit and monitor the amperage draw. Use an amp clamp to measure the current on each leg of the circuit. The total current should be well below the breaker's rating, even with the saw running. Eighthly, test the outlet in the middle building with the circular saw. Observe the voltage and current readings while the saw is running. The voltage should remain stable, and the current should not exceed the breaker's rating. If the problem persists, it may be necessary to call in a qualified electrician to further investigate the issue. Underground electrical problems can be complex and require specialized equipment and knowledge to diagnose and repair. Here are some additional considerations. The use of number 10 American wire gauge wire for a 20 amp circuit is acceptable, and the voltage drop calculation suggests that the installer was mindful of potential voltage losses over the long run. However, it's important to verify the actual voltage drop under load to ensure that it's within acceptable limits. Excessive voltage drop can cause equipment to malfunction and can shorten the lifespan of electrical components. The metal halide fixtures themselves could be a source of problems. Metal halide lamps are known to sometimes fail in a way that causes them to draw excessive current. This is less likely, given the symptoms, but it's worth considering if the over-amperage issue persists after addressing the loose connections. The convenience outlet in the middle building could be a contributing factor. Outlets are often misused, and the circular saw may have been drawing more current than the outlet or the circuit was designed to handle. It's important to ensure that the outlet is properly rated for the intended use and that users are aware of the circuit's limitations. The fact that the problem started after the worker plugged in the circular saw suggests that the saw may have damaged the outlet of the circuit. It's possible that the saw has a short circuit or is drawing excessive current due to a malfunction. It's important to inspect the saw and ensure that it's in good working condition. The replacement of the ground fault circuit interrupter, or GFCI, outlet was a good troubleshooting step, but it's unlikely to be the cause of the over-amperage issue. GFCI outlets are designed to protect against ground faults, not overloads. A ground fault occurs when current leaks to ground, which is a different type of problem than over-amperage. In summary, the most likely cause of the over-amperage issue is a loose connection in the underground conduit, particularly between the first and second buildings. A systematic approach to inspecting and tightening all connections, along with careful monitoring of voltage and current, should help resolve the problem. If the problem persists, it's important to seek professional help from a qualified electrician. To recap the troubleshooting process in a more structured way, consider the following steps. Firstly, gather information by talking to the customer, reviewing the electrical drawings, and inspecting the site. Secondly, ensure safety by de-energizing the circuit, locking out the breaker, and wearing appropriate personal protective equipment. Thirdly, inspect the breaker panel for loose connections, signs of overheating, and proper breaker seating. Fourthly, systematically check each junction box for loose wires, corroded connections, and signs of overheating. Fifthly, focus on the underground conduit runs, using a cable locator to trace the path and identify potential damage. Sixthly, use a multimeter to measure voltage and current at each junction box, looking for voltage drops and high current readings. Seventhly, pay close attention to neutral connections, ensuring they are tight and secure. Eighthly, tighten all loose connections, replace any damaged components, and ensure proper grounding. Ninthly, re-energize the circuit and monitor the amperage draw with an amp clamp. Tenthly, test the convenience outlet with the circular saw, observing voltage and current readings. 11thly, if the problem persists, consider the metal halide fixtures as a potential source of excessive current draw. 12thly, if all else fails, consult with a qualified electrician for further investigation and repair. Let's delve deeper into the electrical theory behind why a loose connection can cause overamperage. According to Ohm's law, voltage equals current times resistance, or volts equals amps times ohms. When a connection is loose, the resistance at that point increases significantly. This is because the contact area between the conductors is reduced, forcing the current to flow through a smaller area. Since the voltage remains relatively constant, the increased resistance causes the current to increase according to Ohm's law. The increased current flow generates more heat at the loose connection, due to the power dissipation formula, power equals current squared times resistance, or watts equals amps squared times ohms. This heat can cause the wire insulation to melt, leading to a short circuit. A short circuit is a low resistance path that allows a very high current to flow. This high current can quickly trip the breaker, protecting the circuit from overheating and potential fire. The problem is exacerbated by the fact that the metal halide fixtures are inductive loads. Inductive loads draw more current when they are first turned on, due to the magnetic field that needs to be established in the ballast. This inrush current can be several times higher than the normal operating current, and it can further stress the loose connection, causing it to overheat more rapidly. The convenience outlet adds another layer of complexity. Outlets are often used to power a variety of tools and equipment, and it's possible that the circular saw was drawing more current than the outlet or the circuit was designed to handle. This is especially true if the saw has a universal motor, which can draw a lot of current when it's under load. The National Electrical Code, or NEC, provides guidelines for the proper sizing of conductors and overcurrent protection devices. For a 20-amp circuit, number 12 American wire gauge copper wire is typically required, but number 10 American wire gauge wire can be used to compensate for voltage drop over long distances. The NEC also specifies the maximum allowable voltage drop for branch circuits, which is typically 3%. In this case, the use of number 10 American wire gauge wire suggests that the installer was aware of the potential for voltage drop and took steps to mitigate it. However, it's important to verify the actual voltage drop under load to ensure that it's within acceptable limits. Let's explore some additional troubleshooting techniques that can be used to pinpoint the location of the loose connection. One technique is to use a thermal imaging camera to scan the circuit for hotspots. A thermal imaging camera can detect temperature differences, and a loose connection will typically show up as a hotspot due to the increased resistance and heat generation. Another technique is to use a time domain reflectometer, or TDR, to locate faults in the underground conduit. A TDR sends a pulse down the conductor and measures the reflections. A change in impedance, such as a loose connection or a short circuit, will cause a reflection that can be detected by the TDR. This can help pinpoint the location of the fault. Another useful tool is a circuit tracer. A circuit tracer consists of a transmitter and a receiver. The transmitter is connected to the circuit, and it sends a signal down the conductor. The receiver is used to trace the signal, and it can help identify the path of the circuit and locate any breaks or shorts. When working with underground electrical systems, it's important to be aware of the potential for buried utilities. Before digging or excavating, it's essential to call the local one-call center to have the utilities marked. This will help prevent damage to underground cables, pipes, and other infrastructure. It's also important to be aware of the potential for groundwater. Underground conduits can sometimes fill with water, which can corrode the conductors and connections. It's important to use waterproof connectors and sealing compounds to prevent water from entering the conduit. In addition to the technical aspects of troubleshooting, it's also important to communicate effectively with the customer. Explain the problem in clear, concise terms, and keep them informed of the progress. Be honest about the potential costs and the time required to complete the repairs. In conclusion, a loose connection in an electrical circuit can cause a variety of problems, including overamperage, voltage drop, and equipment malfunction. A systematic approach to troubleshooting, along with the use of appropriate tools and techniques, can help pinpoint the location of the fault and restore the circuit to proper operation. Remember to always prioritize safety and to consult with a qualified electrician if you are not comfortable performing the repairs yourself.